surface. So for that we have an experiment. So we have a boat traveling in the sea. It carries explosives that are called sources. Each explosion creates seismic waves into the ground, and those seismic waves are banded and reflected, coming back and recorded into an array of receivers, which are hydrophones that record the waves after they travel through the Earth. More schematically, we have the source. It sends the waves to the receivers. The data is recorded in the receivers in time domain. It is processed, undergoes, in our setting, it undergoes a Fourier transform, and we model in frequency domain, we model the motion of the waves by the Helmholtz equation. So we have the Laplacian plus this frequency times m. M is the properties of the Earth that we wish to recover, times u. U is the waveform, and equals delta of x minus x at the source. So this is how we model the explosion at the source. Mathematically, we've got an inverse problem, a PD constraint optimization. So we minimize for m over all frequencies and all sources. U is the waveform that is dependent on m. This is given by the solution of the Helmholtz equation for frequency j and source I at point m. Dij observed is the data for a source I and frequency j that is given, and P transpose projects u, which lives all over the domain. It projects it to the location of the receivers, and we wish to minimize this data fidelity term. This problem is ill-posed, so we need regularization or prior information. And here we've got bounds, which is also prior information, to keep the solution physical. So we know what to expect in terms of the properties of the Earth. We know that it will be somewhat piecewise constant or piecewise linear. So we introduce those terms to make the problem physical, to make the solution physical. So our favorite choice of solution method is Gauss-Newton. So consider again this following minimization. We form an approximation, a first order approximation for u. So u at point m plus delta m is u of m plus j, the Jacobian times delta m. And this Jacobian is a dense matrix. We cannot store it, but we can apply it in a matrix times vector product. So once we plug the linear approximation in, we've got this quadratic term. We have the residual, the data residual here, and we solve this quadratic problem using, say, conjugate gradient. So we can apply J and J transpose vector. So each conjugate gradient iteration, we need to apply J and J transpose. And each J times vector or J transpose require a forward Helmholtz solve. So we've got, at each iteration, we got 2 times n sources times n frequencies, Helmholtz forward Helmholtz solves, and sources can be between hundreds to thousands, and frequencies can be between 5 to 30. So we've got lots and lots of Helmholtz equations to solve. To deal with this problem, we've got a software written in Julia, and this is joint work with Lars. He talked about it yesterday. So it includes electromagnetic and seismic inversions. This is done in distributed computations. It's a generic optimization framework that basically do the 4 problem solves in parallel, which are the main bottleneck of this whole inversion. And the basic version of this software is available in GitHub. So our first task here is how to solve the Helmholtz equation. So in 2D, we use just direct solvers of some available software. It works pretty well. And in 3D, we can do the direct solvers don't scale that well. So we need iterative solvers for this equation. This is a really hard equation. It's indefinite. And there are iterative solvers in the literature. My favorite approach is multigrid, so I'm focusing on that. Currently, this is not a done deal. Currently, we've got two codes to solve that. One of them is what I call the numerical linear algebra approach. So we use the shifted Laplacian preconditioner, but we do it from multiple right-hand sides to get performance. So we've got block multigrid preconditioning, block Rylov methods. We use case cycles. We use all kinds of, you can call it standard multigrid tricks to get this work really fast and really to get every bit of performance from our multi-core machine. We've got also the nonlinear approach, which is still in development. Basically, we have to treat each source separately, and we tailor the solver to the right-hand side. So this approach is definitely more scalable than this approach, but still we require a setup for each right-hand side, and we've got many of those, and this becomes quite costly. At the problem size that we're interested to solve in 3D, this is still preferable, but in bigger dimension or larger dimensions, eventually we'll have to go there, but this is still work in progress. So, this talk is not about Helmholtz, it's about FWI. So FWI is a difficult problem on its own. So it's highly nonlinear, it's very sensitive to the starting point or the initial guess that you put into Gauss-Newton. In the absence of low frequency, the problem is highly ill-posed. So many bad recoveries may fit the data reasonably well. There are lots of local minima, and basically if you consider all frequencies at once, you'll get to a bad recovery or a minimum. And the solution may be constructed gradually from the lowest frequency to the highest. And we do that by a frequency attenuation strategy, which is rather standard. So we apply Gauss-Newton for the first frequency, then for the second first frequency, and then we go on and add more and more frequencies until we solve the problem for all frequencies together. And let me show you an example of how this is done. So this is the SEG model. We have a medium here and the solid body here, kind of a discontinuous model. This was constant, more or less. This is in 2D. We've got 9 frequencies. The lowest is 3 wavelengths, and the highest is 50. So such that the resolution of the mesh allows us to use 50 wavelengths. We've got, at the top, we've got 4 sources, a source every 4 pixels and a receiver every 1 pixel. And this is our initial guess. This is a linear velocity model. And let's see how it goes. So this is the first, this is the good example. This is the first frequency, the result of the first frequency inversion. You see this smooth blob that corresponds to the low frequencies that we had in the corresponding data, and then we go on and sharpen the image by introducing more and higher frequency. Now let's see what happens if we start from the third frequency. So we don't have those low frequencies, and we start from the third one, and this is what we get as our first iteration or initial guess. And when we go on and do the inversion, we get this, which is obviously a bad recovery. It has a name in geophysics. It's called cycle skipping. And this is what we get. So the conclusion is that we must have low frequency data. However, it's impossible to collect this data in the field. So the data is noisy at low frequencies, and we cannot use it. And this is an open question. So let me jump to a different problem, and maybe at the end I'll try to answer that open question. So travel time tomography. This is a different problem that can be obtained from the same data, basically. So here I have a source, and here I have a receiver. So the source, now the receiver records nothing, and the source explodes, and the waves travel, 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 travel. At some point they reach the receiver, and how we see some movement here. The moment where we see that movement is the first arrival of the wave. So it's the time where the wave arrived to the receiver, and the first arrival of the wave can be modeled by this equation. This is a nonlinear equation that is called the eikonal equation. So m is again the properties of the Earth, the slowness of the Earth, and tau will be the travel time that is defined all over the domain. Obviously, at the source, at the location of the source, the travel time is 0. So this is our initial condition for this PDE, which is sort of an advection PDE. Okay, so we've got the forward model. This is our forward model, the eikonal equation, and we've got the inverse, the corresponding inverse eikonal equation. So di observed is the data, the first arrival data. And again, P projects tau to the location of the receivers. This time we've got only a sum over the sources. We don't have frequencies here. The same regularization can be applied. And now we need to solve the forward problem, just as before. Okay, so how do we solve the forward problem? So actually, this is quite, although this is a nonlinear equation, this is quite easy computationally. So there are many solvers in the literature. They are mostly divided into two. There is a fast marching, which is a kind of a direct solver in order of n log n. And there is the fast sweeping approach, which is a Gauss-Seidel, basically. And there are several versions of the problem. So the original equation is just that. And this is where the fast marching method by Session was developed for. But people have realized that because we have a point source, then the solution is not accurate because of the singularity of the source. So this is a solution for a constant medium, and we have a singularity at the source, and this pollutes all our numerical solution. So they came up with a correction, a factored version. So we look for, so it's the same equation, but this time our variable is tau1, which is the factor to tau0, which is this function, the distance function. And this really take out the source singularity out of the equation. So the solution here would be much more accurate than here. That's a known fact. Still, for this equation, there were only fast sweeping methods available, and we developed a fast marching approach for several reasons. One of them is the solution of the inverse problem for this particular travel time. So we've got this paper on the web, and we have that. But let me just briefly describe what fast marching is about. So don't be, this is the discretization. Dij minus y, for example, is the forward, is the backward, first order backward finite difference derivative of the first for the first derivative. Okay, and don't be confused about this this discretization. It's an advection. It's an upwind advection operator. So our goal is to find the direction of the upwind stream, and we start from a known initial value at the source, so tau at the source equals 0, and we march outwards as the wave would propagate in the domain. And so we wish to find the lowest travel time possible, so each time we select the smallest value and propagate forward. So let's see a movie. So we started from the corner, and now we've got a front going on. We've processed all these values. They're done, they're set, and each time we select the minimal value at the front, and we update its neighbors, and this way we swim through the whole domain. Okay, so again, we've got the inverse problem. This is how we solve the forward problem. We've got the inverse problem, and again, we use Gauss-Newton. And what's really good about fast marching is that the Jacobian, or the sensitivities, the sensitivity times vector can be obtained by a lower triangular solve. So I'm not going to show this, but this is the main advantage of fast marching. And now for our main contribution here is the joint inversion of these two processes. FWI on the one hand, travel time tomography on the other. And because travel time tomography is a kind of integration, basically, it promotes, or it has low frequency features. So on the one hand, we wish to relieve some of the dependency of FWI in low frequencies by introducing the travel time tomography. And second, we wish to fit M, or to make M fit both data types. So waveform on the other hand, and travel time on the waveform on the one hand and travel time on the other. So hopefully it will be more accurate. Okay, so for that we introduce a joint frequency continuation process. We treat the travel time tomography, or the eikonal inverse, as a low frequency. So again, we solve for the eikonal in the first frequency, eikonal in the first and third, and so on until we sweep through all frequencies. And again, this is the same experiment. We start from the high frequency. Okay, the same experiment, the same bad experiment as we did before, only with the eikonal as initialization. So this is what we get from the travel time tomography. This kind of, you can see that it has some low frequency features. And we travel, or we continue until we get this relatively good result. And you can see this is the good example, this is our solution, this is the bad example. These two use the same waveform data. This one used the low frequency data, which is kind of not fair, not available. Okay, in 3D, we have a result for travel time tomography. It's a 200 by 200 by 100 grid, 567 sources. I was able to do this with one machine through a night. Okay, in retrospect, this is way too much sources, but still, this was really fast to obtain this. And as you can see, this is a pretty good approximation of the solid body. Still, obviously not sharp, but this can be a really good initialization for FWI. So ongoing development, 3D FWI, we're still working on this. The computer is running, believe me, and we're waiting for results. It's really hard to tweak the parameters when each run takes a week. But still, we're doing that. 3D Helmholtz, well, the never-ending research topic. I'll continue work on that. We've got a stochastic choice of sources, more or less in place now. But still, the previous scenario needs improvement, so it's not robust enough. We wish to start from even higher frequencies, and we wish to recover the salt areas. So in order to address those, this is quite experimental still. For that, we force M to have only low frequencies. And we do that by either high order regularization or some kind of a multi-scale initialization. So consider multigrid. On the coarsest level, you don't have high frequencies. So we say, I don't care about the data is, I'm not letting high frequencies in the door, and let's see what we come up with. So this is with high order regularizations. We basically say we're not accepting high frequencies. And you can see that this, together with travel time tomography and FWI, I got this pretty smooth block, basically, which is used for initialization. This is very similar to what you saw previously with the low frequency. This doesn't fit the high frequency data, it cannot, but still it reduced some of the some of the misfit. And this is the final recovery using really high frequency data. So this is really something that is real. So I've used only frequency values that are available in real life. And this is a true model, of course, and you see the similarity, which is pretty good. So let me conclude. So low frequency data is crucial for initializing FWI. However, this data is not available, and first arrival information is available and can be used to replace the low frequency data by solving the travel time tomography and make them joint, make them together, so they like each other. For a more robust initialization or reconstruction, we used high order regularization. We recover the area underneath the salt body, which is important. And in future work, we're looking at objective based on optimal mass transport. So we kind of want to relieve the non-linearity of the problem. We're looking at joint FWI and electromagnetic inversion, and we're hoping to look at elastic FWI. And we wish to do this all in 3D and large scale. So thank you very much.